So to remind you guys where we left off, we were in this linear betting game that I covered. Again, to remind you of the game, each round you have an amount y hat t. The magnitude of y hat t is what you bet. And the sign of y hat t is kind of whether you're placing your bet on team A or team B. And the outcome yt is revealed for the match between A and B. If A wins, then yt is +1. If B wins, yt is -1. And what your loss is basically the amount of money that you lost, right? So it's minus yt times y hat t, meaning that if you got it right, then your loss is negative, meaning that you gain money. And if you got it wrong, then you of course lose money. Okay. Yes, so if you wanted y hat t to be bounded by a specific number, it's pretty much the same. Right? If it is bounded by 1, then it's exactly the same, or kind of you'll have. It's roughly the same. I mean, it's equivalent. So maybe you can rewrite it differently, but it's exactly equivalent. So the main thing here is we are not allowing, I mean, we are not restricting it to be kind of bounded, which is what helps us remove the condition that we talked about, the stability condition. Okay, and also the other difference here is, so earlier kind of y hat t was either +1 or -1, and it was drawn from qt. Here y hat t is a real valued number, right? So this loss I mean, the loss is linear in y hat t. And this has an advantage that now you don't need a randomized algorithm, it's a deterministic algorithm works. And that's basically what the result that kind of we sketched out earlier. It says that you give me any function phi. Oh, I guess I still haven't corrected the slides, I should have. This should have been y hat t minus y hat t times yt. So the loss over the n rounds is upper bounded by phi of y1 through yn, if and only if the expected phi under epsilon is greater than or equal to 0. Okay? And again, A, which is the top quantity here, implying B is simple, because this is true for every single y1 through yn. Take it for epsilons, which are Rademacher random variable, that will imply B. B implying A is the harder part, and for that you use specifically the strategy here. And the high level idea was that you kind of start from all the way from n, and you notice that at round n, it doesn't matter what the opponent played, right? Or in other words, it doesn't matter who won the game, because what you can show is that minus y hat n times yn minus of p of y1 through yn, we showed that for the specific strategy given there is exactly equal to expectation over epsilon n minus phi of y1 through yn minus 1 comma epsilon n here. Okay, and the idea here is that it doesn't matter what the adversary played, you always get kind of your current loss plus the cost to go is always equal. And typically these kind of strategies for y hat n are called equalizers. And because here we are facing an opponent in a zero-sum game, the fact that it's an equalizer is already a certificate that it's the optimal policy. Okay? And now kind of working backwards, you can conclude, as I already mentioned, that minus y hat t times yt minus phi of y1 through yn is equal to minus expectation epsilon 1 through epsilon n p of y epsilon 1 through epsilon n. The idea is kind of you just apply this recursively. So replace this quantity by this, add the next loss, the n minus 1th loss, and so on. Yep. So if you have a min-max game between two players, that's a zero-sum min-max game. And if you can demonstrate that for one of the players, if you can demonstrate that there exists an equalizer strategy, then the equalizer strategy turns out to be the min-max strategy. And you can show that the value of the game is, it's a theorem from kind of classic game theory. I'm just mentioning it. It's not, I mean, I kind of, so by plugging in the strategy, kind of, I just showed you guys how it works. But it's also a certificate that it is the optimal value. And you can also work it out. So the way to work it out typically is kind of, you want to, I mean, at the very last step, you want to get the optimal policy here, right? So that means that I want to do min over y hat n. But as a player, I get to kind of go before the next player, right? And then the max player would do max over yn belonging to plus minus 1, right? And then you look at this quantity here. And now if you derive the minimizer out here for this function of yn, sorry, this function out here, that turns out to be exactly this strategy here. And that's kind of how you, here I just kind of, I skipped the step and I directly plugged in the right solution, but this is the way you derive the solution. Yeah. For this game, yes. For the betting game, you can have a deterministic strategy. That's because you're allowed to bet kind of all the way to even just $0 or 0 rupees or whatever, right? So you don't need to necessarily bet kind of either 1 or minus 1. And so because you have this kind of, you have the choice of how much money you plan to bet, so that allows you to kind of get away with doing a deterministic strategy. But kind of the mathematical way to think about it is that my loss, I guess, I'm sorry about the error here, but the loss here is this guy, right? It's linear in y hat t. So whenever you have a linear loss, it doesn't matter whether it's randomized or not, because even if it is randomized, you get the same loss or the same regret if you played the expected value of that loss. Okay. All right, so this was what we had. Huh? Uh-huh. Mm-hmm. Right. So here, no such thing is, I mean, it's not directly guaranteed, right? It is a bounded function. Right. So, okay. So the question is, what happens if I want to pay? So imagine that on every round, I don't exactly get this right. So instead I kind of do, I mean, I take one single draw, right? Now what's going to happen is that, let me think about it. So if I had, so the issue that you're going to have is that you're going to have these errors as additive, right? If you have these errors as additive, that can pretty much kind of get rid of the square root n type bound that you were hoping for. It gives you linear in n. So you need to have some extra properties of phi to get useful bounds. But we'll kind of, for now, let's just say that we can compute this. Right? And the thing is, even if you cannot, I mean, single draw might be hard, but you could still do things like I take a few draws and then approximate it, you might get like better error rates. We'll also see if there are other strategies as we go along. Yes, but the thing is, we don't want to assume anything about that constant, right? Like I don't want to say that it's bounded by 1 or b or some fixed constant. It could be bounded by some very large thing, right? So that's the whole point of this, right? If I replace 1 with b, maybe, yeah, I could still get away with b root n, but I don't want to necessarily do that. All right. Okay, so this was, I guess, the question that I left you guys with. Which was the following. Let's think about a simple kind of betting game where we have m teams that want to play with each other. Okay, and let's say that which pairs, and these are kind of pairs of teams playing against each other, right? Team A plays with team B and so on. And let's say that I actually tell you the pairs that are going to play with each other for the n rounds in advance. So I'm going to tell you team I1 and team J1 all the way up to team IN and team JN play with each other for the n rounds, okay, where each of these I's and J's belong to one of the M teams. Okay, so I'm giving you these the sequence of matches in advance, and what I'm not giving you is what's going to be the outcome of the game, and that could possibly be adversarial, but at the very least, we don't really want to put any assumption on what's going to be the outcome of the game. Okay, and the benchmark that we want to look at is the following. I want to basically say that my loss or my gain is not much worse than the loss or gain if I had kind of seen the outcomes of all the games in advance, right? If I knew all the n games that happened between these pairs, and then for each player or each team in this m teams, I choose a score for them. Let's call that W1 through WM. And whenever the teams I and J play against each other, I'm going to bet the amount that is given by Wi minus Wj, meaning that the magnitude of my bet is Wi minus Wj's magnitude. And which team I'm going to bet on is going to depend on whether the score of I is larger than J or not. Yeah. No, Wi is, so I'm just giving you, so there are M teams, right? So W1 through Wm are just M numbers in the reals. So this is kind of what this is our benchmark. So if you told me, so let's say that we are talking about a cricket tournament, right? And let's say that I even give you the order in which the pairs of teams are going to play, right? And now after the games have all happened, I'm going to look at kind of after all of the entire series is done, I basically go and let's say rank or score each of the teams, right? I say, oh, this team has like this much score, this team has this much score, and so on. And now I get to choose that in any way I want. I'll give you one small restriction in the next line. And then what I'm going to do is that whenever team 1 plays with team 2, I'm going to bet the amount given by the difference in their score. And it's going to go to either, I'm going to bet on team 1 or team 2, depending on which score was higher. If team 1's was higher, I bet on team 1. Yeah. And I'm going to also put one restriction that the maximum bet value allowed for this benchmark is going to be capital B, meaning that the difference between any two coordinates should not be larger than capital B. Okay, and why do I need this B to be fixed? Because I could basically, if I didn't have such a fixed value, then there's no way any strategy would work. Because essentially I could just pick, for instance, whoever the winner is, and then just give them like a whole ton of money, right? And I mean, if you as a learner, like you don't know who's going to be like the top team, you are going to bet some money. I'm going to basically bet much more than whatever you bet throughout, all on just the winning team and just between like the first and the second teams, right? And then so there's no way I can kind of compete. So there has to be some kind of restriction on what's the maximum allowed bet value. And that's this capital B that we write down. So in math, the way we write this down is that my regret is sum of my losses, which is y hat t times yt, negative of that. I want this to be as good as min over all possible scores between of these M teams, such that for any two teams, the value is not much more than capital B. And then I just look at the sum of minus yt times the bet amount given by wit minus wgt. Okay, that's what I want. And so the reason I kind of brought this up is to give you like an example of how kind of you can use coerce result to get something interesting out here. Right? So if this was the regret that I was aiming for, we can directly plug this into, I guess, the extended coerce result, maybe let's call it, that will give us something useful. Okay, so in this case, we can write down what the phi function is. We want to compete with this benchmark here, but we don't know if this benchmark that I just mentioned in the previous round, right? So in the previous slide, so this is our benchmark out here. I want to compete with this guy. So I'm going to write down phi to be this guy plus some value c sub n, and we're going to ask the question, what's the best or smallest c sub n that will allow this function phi to be admissible, meaning that there is some strategy that can always get the regret bound that I want, right? So what's the best c that we can hope for? And we already know how to compute this, right? Because our lemma basically said, sum t1 through n minus y hat t times yt minus phi of y1 through yn, or let's just call it, is less than or equal to yn if and only if what? Expectation phi of epsilon is greater than or equal to 0, right? And so let's just plug that phi in, and that'll give us what the value of Cn is, right? So in expectation over epsilon, we look at min over w in w such that for all I comma j, wi minus wj is less than or equal to b minus yt times wij minus it minus wj, right? And then plus Cn, this whole quantity should be greater than or equal to 0. Or in other words, Cn should be minus the expected value under epsilon. And now you can do a little bit of manipulation out here So the first thing you notice is that the bet values have to be less than or equal to B. So I can write this. Okay, the first thing I did was pull this minus out here inside the min, so that becomes a max, right? Minus min is same as the max. So that was the first step. The second step is that if I consider all vectors here, but I'm only considering difference between coordinates, it suffices for me to just take W belonging to 0, B to the M, right? Because between any two coordinates, it can be at most B and can be any value between 0 and B. So I get this simplification on the next line. And then finally, what I'm going to do is I'm going to collect. So we have a sum over T terms, and you have these teams IT and JT playing against each other. Right? What I'm going to do is I'm going to rewrite this sum into two pieces. I'm going to collect all the times that team I played. So I'm going to sum over all the teams I from 1 through M, and then collect all the times that team I played, and then I'm going to rewrite it this way. Okay, this is going to take, I just want to make sure that it's clear what's happening here. This is just another way of rewriting this sum, right? Because every time Wi comes here, that's accounted for in one of these sums from I from 1 through M, right? And whether it comes with a plus or minus depends on whether it comes whether IT is equal to I or JT is equal to I. And because I'm summing over all I from 1 through M, this sum is equivalent. Now from here, notice that this maximum can be divided into all these M coordinates separately because they're just M separate maxima. And so finally, what you would get after doing all of this is that essentially I get B, which is the maximum amount that you're allowed to bet. That the benchmark is allowed to bet, times the expectation over epsilon 1 through epsilon n, sum over each of the teams. And for each of the teams, I basically sum over epsilon t, where I sum over epsilon t only up to ni number of times. That is, in other words, for each team I, ni is the number of times that that team plays, right? So let's say that team 1 played 20 matches overall in these n matches. I'm going to sum over separate epsilon t's from 1 up to this 20 for team 1, and I do this for each of the teams. Okay, and I take the max between the sum of these epsilons and zeros. And what comes out of this is essentially a quantity that you can work out looks like B over 2 times square root M times N, which means that we only pay square root of number of rounds that we played or number of matches that we predicted, and it only depends square root number of teams that are playing against each other. Okay, the last step here between here to here is just a Jensen's inequality, because you can kind of divide by M and think of this as an average, pull this inside the square root. Okay, so that's kind of a result that you'll get automatically. But of course, here I'm assuming that the teams that are playing with each other, I'm kind of told that in advance. So the next question we want to ask is, what if we didn't? Yeah. So up to this step, it's pretty much tight. This step to this step, it's asymptotically tight. Up to constants, it's tight. Okay. All right. So the next question that we want to ask is, what if we didn't know which teams are playing in advance, right? If you think about an actual cricket tournament, it's not going to be that kind of we are in advance, we are told what are all the teams that are going to play with each other. On the first round, yes, we are told which teams play with each other, but then depending on who qualifies, only the qualifying teams play the next round, right? So there is the decision of even who plays against whom is decided by who wins on the first round and so on. And so the next question that we want to ask is, what if we didn't know who played in advance and somehow this was given to us on the fly? Okay, and we can actually generalize this much more by putting in arbitrary covariates or arbitrary context. Okay, so this is kind of a more general version of the betting problem that I talked about, and it starts getting into more kind of real on the field kind of learning theory setups. Okay, so in this case, on every round, first you're given a context xt from some arbitrary space script x. Okay, so we are told, so think about xt as your input instance, right? So if you're thinking about, like, let's say predicting whether an image has a cat or a dog, xt can be thought of as the image that you're given. Okay, so first you're given this context xt, then the learner has, it's kind of again the same problem. The learner has to place a bet. It's represented by y hat t. The magnitude of the bet is the amount. The sign is going to be whether team A wins or team B wins. And now the outcome of the round is revealed to you and you pay the loss as before. The only difference here is this function phi, our benchmark out here, is not just going to be dependent on y1 through yn, it's also dependent on these contexts x1 through xn. Okay, and a simple example of the context. So, I mean, if you look at the previous example, there xt could just be it comma jt, and it's told to you kind of as you go along. So as you come to the tth round, you're told which two teams are going to play against each other. But more generally, even if you think about the bit prediction problem, you could think about xt as just being the vector or kind of some representation of y1 through yt minus 1. Right? So you're saying that now I want to kind of compete, I mean, I want phi to not just be aware of, I mean, not just be a fixed function of y1 through yn, but somehow also take in as context what happened in the past. Right? And so this starts getting into more kind of complicated strategies that you would want to kind of compete against. Okay. Yeah.
The bit prediction, we try to do strategies that work against all of this.
Yes.
Even those are the things which consider the context.
Mm-hmm.
So what
but in the bit prediction, by saying that phi is a function of y1 through yn, right? In some sense, that was already kind of limited, right? So we are not allowing for, I mean, yeah. So I guess, okay, so if I basically, so in the bit prediction problem itself, like so there's a betting problem and then the bit prediction problem. In the betting problem, yeah, you could make phi to be an arbitrary function of y1 through yn, right? But I guess here we want to kind of capture the notion of context, which is not necessarily only these guys. So for a bit prediction, you could put this as context, but more generally, the context could be like external side information. In the bit prediction, like the original bit prediction problem where you needed stability, if this was the context, you're not going to have stability. In the linear betting, it's not an issue. Here, of course, we are kind of considering the linear betting setting. So we are kind of removing this stability requirement. And then next is, instead of just saying that our context is just this one. So as an example, you could take this, but more generally, xt could be any external information, right? So for instance, xt could, for instance, be like you read the newspaper and then it tells you how the teams are preparing on each day, or kind of if there was an injury to some player and so on. All of those you could kind of have in the context of xt. Right? So it can be much more than just y1 through yt minus 1, but it could definitely be y1 through yt minus 1. Yep. Right. Yes. Right. So, okay. So in some sense, what we choose as benchmark, this phi function, is important, right? So Cover's theorem basically tells us which phis are possible to get results for and which are not. But of course, ideally, I would want the phi that's kind of the most, I mean, where I could kind of compete with almost everything under the sun, but such phis are not going to be possible, right? So in some sense, there's a balance between kind of how rich your phi is in terms of kind of how well can it capture the benchmark or what's like the right benchmark versus whether that phi is even achievable or not. So Cover's result just shows, I mean, just talks about whether it's achievable or not. The other side of it, we can even see through an example. So if you remember kind of the script F, right, the set of models, that how rich script F is the other part of the game, right? The richer it is, for Cover's result, it's worse because it says that you get bigger and bigger bounds. But the richer it is, it also means that the benchmark is better, right? So there is kind of a trade-off there. And I guess in classical statistical learning theory, this is kind of typically like the overfitting versus underfitting, or kind of the sample complexity versus representation power, kind of parameterization, your power of your parameterization kind of trade-off. And that's the exactly same thing here. Cover's result kind of covers the sample complexity part. The richness of phi is kind of will tell you whether this benchmark is good enough or not. And you need to strike a balance. And in the previous example, I just kind of, my tacit assumption while giving you that benchmark was that such a benchmark is good. And that's kind of, I'm basing it off the fact that, oh, maybe kind of there is a strict ranking of the teams. And I can also give them some kind of score that's representative in terms of what's their kind of, how likely they are to win. Right? Of course, that is an assumption, because it might be that, for instance, it might be that if you just take an overall ranking, you'll get a particular ranking of teams. But then whenever team 1 plays with team 23, team 23 always wins because of some other effects and so on. And in that case, you're not capturing such a scenario. All right. So once we start putting in context, then you need to kind of up your game in terms of how these complexity measures are going to look. Okay. So we're going to define this notion of a X-valued binary tree. It's just a fancy name to, it's just a fancy name for a sequence of mappings x1 through xn, where each xt maps from a bit of length t minus 1 to the set script x. Okay. Visually, I like to see it in this following form. You can think of it as a binary tree where in each node sits an element of script x, and basically the plus minus 1 values that you kind of put tell you which path it is. Okay, so in this example, for instance, this entire tree is the bold x here. That's the tree that I'm kind of thinking about here. And in this case, x1 doesn't take in any value, I mean any input, because t minus 1 is 0, and that's just a constant mapping to x1 here. x2 of plus 1 is going to be x3, x2 of minus 1 is going to be the small x2. And similarly, x3 is going to take 2 bits in, plus 1, minus 1. So if it is plus 1, then first go right, minus 1, then go left. So it's going to be x6 here. Okay, that's the way to kind of parse the tree or kind of read how the tree looks. So whenever it's, so the norm that I'm using is for you guys is whenever it's plus 1, go to the right. Whenever it's minus 1, go to the left. Okay. And then the index that you put here in the sequence. So if the index is 1, or if, in general, if the index is t, it only depends on the past t minus 1 bits. Right. So x1 is just what's on the root. Why is x2 of plus 1 equal to the small x3? Because it's x2 of plus 1, which means that go to the right. What's on the right? In this node sits x3, right? And that's about it. So that's just the definition of kind of how to parse this tree bold x here. And now it turns out that this tree is kind of required for our result. So specifically, the extension to this kind of arbitrary covariates is the following, that for any phi that maps from x to the n cross plus minus 1 to the n, there exists, to the reals, there exists a strategy that can guarantee that, oh, again, I put the prediction, sorry, let me write it here. So I'll just write the lemma here. For all phi that maps from script x to the n cross plus minus 1 to the n to reals, there exists strategy such that sum t from 1 through n minus y hat t times yt is less than or equal to phi of x1 through xn, y1 through yn. This happens, let's call this A, if and only if B is true, which is expectation epsilon 1 through epsilon n. Sorry, I need to put the infimum over all trees x. And while writing on the board, because I'm not good at writing these bold ones, I'm going to put a dash on top. And in the slide, it's just the bold one. Infimum over all trees of binary trees of their depth n of expectation over epsilon 1 through epsilon n. Okay, so a strategy exists for us to get this bound if and only if for the smallest tree x in expectation over epsilon. So essentially we are taking a random path and a random choice of epsilon 1 through epsilon n. it's true that, oh, I didn't write what this is supposed to be. This guy is greater than or equal to 0. Okay. So if you didn't have any context, this is exactly the same result that I showed you in the previous or 2 slides ago, in that you don't have the x's here and you're just looking at expectation over epsilons. It's exactly the same thing. And now once you have these contexts, then you start getting these trees in here. Okay. That's the result. And let's quickly look at why that's true. Sorry, where are you getting the phi, like multiple phi's? Where there were no I mean, if the contexts are not there, then you can just put like null for each of these guys, right? Then it's exactly the same. You can kind of think of it that way, but the thing is, it's not like prefixed phi's, right? Because you're interested in taking this infimum over x and then expectation over epsilon of this guy. So this is specifically you're thinking about the case where xt is y1 through yt minus 1. Right? I mean, as I've described here, x's could be arbitrary, right? They are just some absolutely arbitrary context given to you. The only thing you're told is that x belongs to script x, right? So as I was telling you, kind of, you could think about it as like x, for instance, could be like, I don't know, like some kind of health parameter or kind of other parameters of the players. I think if you just try to enumerate them, you're going to lose the structure that you're getting for the phi in here, right? Because phi is also a function of x, and you're not considering just phi on every single x. You're taking expectation over epsilon, right? So you get different paths based off of the different x's that you get. So there's a lot more structure there. I'm not sure how you would capture the structure by defining it that way. And maybe there is, but I don't see it immediately. All right. Yeah. Okay, so the first part of the proof, as before, is fairly straightforward, that A implies B. So we want to say that, oh, what happened here? Yeah, okay, we want to say that A implies B here. And how do we do that? So earlier we just said, let's just play the randomized strategy for y's, which is epsilon 1 through epsilon n. We're still going to do that, except that while doing that, we are also going to choose the strategy for the x's. Because remember that this time the x's are also chosen by the adversary or by kind of the data generating process. So what we're going to do is pick any x bar, tree x bar. Then we have from A that some P from, okay, sorry. So pick any x bar, comma, epsilon 1 through epsilon n. Then we have from A that some P y hat t times epsilon t minus phi of x bar 1, comma, x bar 2 of epsilon 1 all the way up to x bar n of epsilon 1 through epsilon n minus 1, comma, epsilon 1 through epsilon n. is less than or equal to 0, right? So A implies that for any X bar that I pick, if the adversary played the following strategy, so adversary first picks the root of X bar, that's X1, right? And then next, the adversary flips a coin epsilon 1, and then decides whether it's going to be, I mean, once you flip the coin, you either get a left or right. So you're going to fall for X2, you're going for the second X on day 2, you're going to provide X2 of epsilon 1, right? I'm allowed to do that as an adversary because I first played X1, then I flipped a coin that was on previous day. I can look at what happened in the previous day and then pick my X2 based off of that. Then I flip the third coin, oh, sorry, I flip the second coin epsilon 2. Then I'm going to provide, so the adversary strategy is pick X bar 1, then flip epsilon 1, pick X2, the small x2 equal to X bar 2 of epsilon 1, and then flip epsilon 2, and then so on, right? Pick X3 equal to X bar 3 of epsilon 1 comma epsilon 2, and kind of do this all the way through, okay? And if you did that, then what we are guaranteed is that because for any sequence we are guaranteed this, you get the following bound here. Okay, and now just take the expectation over epsilon, and what you would get. First, notice that this quantity disappears because it's a y hat t does not depend on epsilon t, and epsilon t is plus minus 1 with equal probability. So this disappears, and you just get that minus expectation over epsilon 1 through epsilon n, phi of x bar 1 of x bar 1 comma x bar 2 of epsilon 1 all the way up to x bar n of epsilon 1 through epsilon n minus 1. On n, this whole quantity is less than or equal to 0. Or in other words, you can take the negative on both sides, you can flip it. And now the next thing you can also notice is that the choice of X bar was arbitrary. So we can pick the choice to be the worst one, right? And so that basically gives us this condition out here. So that tells us that A implies B. Okay? All right. Now for the other part, I don't want this here, so let me see if I can do it out here. Now for B implies A, do the following. Take P of x1 up to xt minus 1, actually comma xt, comma y1 up to yt minus 1, to be equal to infimum over x bar t plus 1 up to x bar n, expectation over epsilon t plus 1 up to epsilon n. Actually, I should be doing maybe a supremum here. X1 up to x t, comma x bar t plus 1 of y1 up to y e. Sorry, let me see if I can write this up. Minus t. Epsilon t up to epsilon n. Okay, so what we're going to do is for the x1 up to xt, plug in x1 up to xt. But then for the future guys, basically take the worst case tree and plug in x bar t plus 1, where the first t bits are going to be the y's that were played, and the remaining are going to be the epsilons that you generate. Okay, and let's define this as p of x. And then the claim is that we're going to do kind of what we did earlier, in that we're going to show that y hat n times yn minus of this guy plus p of x1 y1 up to xn yn. For all yn, this guy is going to be exactly the same as p of x1 y1 up to xn minus 1 comma yn minus 1. Okay, that's the first step. So we're going to kind of show that the following is true. And let's see. So the way to do this is we're going to look at what's the best I could play against the worst that yn could play. So min over y hat n, max over yn. So we go first, we play y hat n. That's going to minimize for the worst adversary here, minus y hat n times yn. Minus phi of x1 up to xn, y1 up to yn. Right? So at the very last round, this is the optimal thing for me to do. Play the y hat n that minimizes this guy. And then irrespective of what yn is played, if for the worst yn that's played, this is going to be the value of my current loss at nth round minus phi of x1, y1 up to xn, yn. Right? And now you can work this out. So this guy is going to be min over y hat n. And then the max is going to be of two things, right? It's either yn is plus 1, which is going to give me y hat minus y hat n minus p of x1 up to xn, y1 up to yn minus 1 comma plus 1. So sorry, I should write a max here. Between this guy and plus y hat n minus phi x1 up to xn, y1 up to yn minus 1 comma minus 1. Okay. And now we are trying to find a y hat n that minimizes the max of these two guys. And one thing to note here is that this quantity is behaving like minus y hat n. It decreases with y hat n. This quantity increases with y hat n, right? So what's the minimizer here? The minimizer here is going to be the y hat n that exactly equates these two sides, right? Because one of them is decreasing with y hat n, the other one is increasing with y hat n. So, and because I'm trying to minimize the max will occur exactly when these two guys are equal. Or in other words, minus y hat n minus phi of x1 up to xn, comma, y1 up to yn minus 1, comma, plus 1 should be equal to y hat n minus phi of x1 up to xn, comma, y1 up to yn minus 1, comma, minus 1. Okay, we get this equality. That gives us the strategy that y hat n is equal to 1 over 2 times phi of x1 up to xn, comma, y1 up to yn minus 1, comma, minus 1, minus phi of x1 up to xn, y1 up to yn minus 1, comma, plus 1. Okay, so that's, I just solved for what y hat, the optimal y hat n is. Now to get what this value is, you can just plug back this y hat n. Okay, and if you do that, what you will end up getting is that this guy is, I'm not going to kind of work it out because we already did this once for the course result. But if you did this, what you would get is expectation over epsilon n, p of x1 up to xn, y1 up to yn minus 1, comma, epsilon n. Okay? So that's what you end up getting. Now there is one crucial step that we need to look at, in that after doing all this, this was at the nth step, right? Now for the n minus 1th step, what would happen? So at the n minus 1th step, basically the adversary is not just going to pick. So at the nth step, after looking at xn, this is what the adversary would play, right? And this is the value that you get. But the adversary also wants to make this as large as possible, right? So the adversary for the n minus 1th step, we want to make sure that this is not just this guy here. We want to make sure that this happens for the worst xn, right? So the value or what the adversary can kind of hold us to is a max over xn here. And so we would essentially get this equal to max over xn. Yeah, because if you think about what the adversary would do, the adversary would first pick the worst xn, then we pick the best y hat n, the adversary will pick the worst yn, right? And so at the nth step, this is what we are left with. Okay? And now essentially what you kind of do to continue the proof is this was the nth step. Now continue exactly this all the way down from nth step all the way down to 0th step. And what you would get is the following. Irrespective of what x's and y's the adversary picks, you would get that sum t from 1 through n minus y hat t times yt minus phi of x1 to xn, y1 up to yn, or the optimal strategy would basically be equal to supremum over x1, expectation epsilon 1, supremum over x2, expectation epsilon 2, all the way up to supremum over xn, expectation epsilon n, of phi of x1 through xn, epsilon 1 through epsilon n. Okay? Okay, so now I'm going to make the following claim, and I'll give you guys 2 minutes to think about why this is true. Okay, before I go there, so at the nth step, is the reason for the supremum over xn clear, or the max over xn clear? No? Okay, so the max over xn comes because, so think about it as we are basically playing a game against an adversary, right? The adversary first picks an x1, then we pick a y hat 1, then the adversary picks a y1, and then we kind of do this all the way up to the nth round. Now, at the nth round, what would happen, right? At the nth round, so imagine I was given an xn. If I were given an xn, what is the y hat n that I'm going to pick? I want to pick a y hat n that minimizes this quantity, right? Why do I pick a y hat n that minimizes this quantity? Because all the losses that have already happened have happened. The only thing that's left is the loss for the nth round and whatever this benchmark is, right? And I know that the adversary is going to do the best that the adversary could, right? So the adversary is going to have a max over yn. And I'm going to have a min over y hat n because given all the information that I have, I want to make sure that my whatever this loss is or regret is as small as possible. Now, the same reason is why the adversary would pick the worst xn, right? Because at the beginning of the round, what's the xn that the adversary would choose? The adversary would say, if I played the best and adversary picked the worst yn, for such choice of yn and y hat n and yn, what's the worst x that I could kind of inflict? That's max over xn, right? And that's exactly this max over xn. It kind of carries through here with the strategy that we wrote. It becomes max over xn expectation over this final epsilon n. This step here with the epsilon n is exactly what we've been doing before, right? For the course result without the context. You kind of did this y hat n as the half times the difference, and this is how we got it, right? And now kind of continuing the same way backwards, at every step, the adversary is going to try to say that I'm going to inflict as much pain by choosing the worst xt's at every round. That's the max over xt. The expectation over epsilon is coming from exactly the steps that we took there, right? So in the end, you would get this long sequence where you have the adversary picks the worst x1, expectation over epsilon 1, worst x2, expectation over epsilon 2, all the way till the end, right? And that's the total kind of, that's exactly the equality that you get for this quantity here. Okay? Now, the final step here is the simple claim that this quantity is exactly the same as just picking the worst case tree x bar and then taking expectation over epsilon 1 through epsilon n, p of x x bar 1 up to x bar n of epsilon 1 through epsilon n minus 1, comma epsilon 1 through epsilon n. Okay? And this is fairly straightforward to see why these two quantities are equal, because either you kind of, on every round, I kind of say what's the next xn that I can pick, or you can basically say there are only 2 to the power of n paths, and I just look at every path and pick the worst for each one, right? And so these two are equivalent here. And so effectively what we have shown is that our regret is upper bounded by supremum over the tree of expected phi function here, okay? But this implies our premise, because if we know that this quantity, this is the best we could do, and we know that this thing is, this is from, and we know that this thing is upper bounded by 0, then what does that mean? So we already know that this quantity here for the best strategy is exactly this guy here. And from what B tells us, we know that this thing is greater than or equal to 0, put a minus in there, and that just becomes supremum, right? And so that gives us our final form here. And maybe I'm missing a minus. This is all supposed to be with a minus phi here. So all the way till there is all exact equality. You're saying why is from here to here an exact equality? So let's do it in 2 steps. Let's say that the max was achievable, so I don't want to deal with supremum. Then the idea is that what's the worst case tree? First let's look at this quantity. What's this quantity doing? It's paying the worst x1, right? So let's say this max was achievable. Let's call that one x1 star. So I'm going to put a tree where x1 star is the root, okay? Next, I take expectation over epsilon 1. If epsilon 1 is plus 1, then I would have gotten some supremum here, something that maximizes here. And if epsilon 1 was minus 1, I would have gotten a different one that maximizes here, right? Let's call it x star 2 and x star minus x star 2, right? So I'll put those two guys here. X star 2 with a minus and x star 2 with a plus or whatever, right? And then kind of keep on doing the same, right? So what I've shown is that this supremum is achievable by some tree, right? On the other hand, if you did have a tree, then you can also show that that thing is upper bounded by the supremum, right? Because on every step, you're only making it worse. So that basically says that the two are equivalent, right? This is with a max, you could do this. If it is a supremum, then you'll have to basically do the limiting argument. Say that it's not max, but you can take the limit of epsilon tending to 0 and then kind of do it. So that's the steps. All right. Great. Okay. So now if we come back to our example that we've been looking at, where let's say that I kind of fix a model class. So X's are some context, and I want script f to be a model class that says that for every xt, f of xt is going to kind of indicate the score for that bet, right? Or kind of what amount that I'm going to put for that bet. And now if we consider this example, then the natural phi that I'm going to ask is min over all f's in the model class script f, sum t from 1 through n minus yt times f of xt. That's the best model in my model class. That's how much loss it's going to pay. And I want to ask kind of if this was what I wanted to compete with, then what's the smallest Cn that I'm going to be able to afford, right? So we want to kind of solve for what this Cn is. And we do exactly the same thing. And basically, if we do this, we get the following guy. I forgot to put the supremum over x bar x here. So we get the following. Cn of f. So what you will get is Cn of script f is equal to supremum over x bar, expectation over epsilon 1 through epsilon n, supremum over f in script f, sum t from 1 through n, epsilon t times f of x bar t of epsilon 1 through epsilon t minus 1. Yeah. So what I'm missing here is out here is that this is supremum over all the trees bold X. Okay, that's the bound, that's the best bound that you can get. And this tells us that that's the optimal thing you can get. And this one is, the term out here is called the sequential Rademacher complexity. It's very close to closely related to the statistical Rademacher complexity, which is typically what's used in statistical learning theory. Okay. To give you a sense of what Rademacher complexity is trying to compute, which I guess I didn't do in the first part of the lecture, I wanted to start with an example. So let's say that in this case, the input space is just the interval from 0 to 1, and the class script f is a bunch of these about 4 functions. Okay. Now, what Rademacher complexity does is the following. You give me a sequence of x1 through xn. So let's say x1 sits here, x2 sits here, xn sits here, x3 sits here. What it's going to do is the following. For each of these x1 through xn, it's going to draw an epsilon 1 through epsilon n. Right? So the first time I draw, maybe it puts x3 as -1, xn as +1, x2 as -1, and so on, and x1 as +1. And it's going to say, amongst these 4 functions, which is the one that correlates most with these red dots here, right? Which is the one that fits it best. And in this example, it's going to be this red one here. Amongst these 4 functions, it goes closest to these red dots. Right? And then I do this repeatedly for every choice of epsilon 1 through epsilon n. So if the next choice was -1 for x3 and +1 for x3 and -1 for xn, x2 and +1 for x1, then this function is closest, and we're going to take an average over all of these guys. Right? That's the classical Rademacher complexity, where you just you take the worst case of sequence x1 through xn, and you do this following here. Now, there is a difference between that guy and what we are looking at here, because here the x's depend themselves on the past epsilon 1 through epsilon n. Okay, so if you want to think about this as pictures, through pictures, take the same same input instance script x as just being interval from 0 to 1, take the same set of 4 functions, but let's look at how the sequential complexity is different. So here, first of all, we start with a tree. Let's take an example, this tree out here. Okay. So this is a tree out here. You get x1 all the way up to x3 in this example. And then what I'm going to do is the following. First, always I take the root. So I take x1 that, let's say, sits here, and I'm going to draw an epsilon 1 through epsilon n. Then what do? I first put a +1 there, right? And I not just do that. Once I get a +1, I'm going to go to the right because it's a +1. So the next thing I'm going to go for is x3, right? So that's this guy out here. I draw an epsilon 2. Let's say that's -1. So because it's -1, I go to the left. I get an x6. And then I basically do the same procedure all the way down to the depth. The difference here is that for each draw of epsilon, I get a different input sequence x1 up to xn that depends on this path on this tree here. Okay, and on average over these draws, how well does my function class correlate with these epsilon 1 through epsilon n on the specific path? That's exactly the quantity that we are measuring. It turns out that that's the right quantity when you have adversarial kind of inputs. Okay, so the final connection that I wanted to do before moving on to the next topic is, so the way I kind of presented it, I presented it as if it was this betting game, right? But it turns out that even just this betting game is like fairly more general in that you can reduce quite a few problems to this betting game. Yeah. Yeah. Mm-hmm. So it turns out that for this one, you can also get exactly the same bound. Okay. And it turns out that, so a few things maybe I'll just note because I'm not doing it here. So it turns out that if you turn this crank there, you can pretty much get the same bound. And in fact, you can kind of write down that problem like, so notice that on every round, you get IT, JT pair, right? And then your loss is W of IT minus W of JT, or like that's your prediction times epsilon T, right? So because it's of this form, you can actually write it down as, you can kind of think about, instead of me writing it down as IT, JT, I can write down XT as being EIT minus EJT, where the E's are the basis vectors. And now I can think about my prediction or my benchmark as W transpose XT, right? So it's in fact a linear kind of, not just convex, it's a linear form. So it turns out that if you use this, and you do gradient descent, you would get something like online gradient descent, which I'll talk about maybe later. It's an algorithm that's commonly used. If you know gradient descent, you know online gradient descent. It's just like if you know SGD, you know online gradient descent. Okay, so you do that, and what you would get is essentially the square root n times like m outside of square root. And then if you do if you've heard of the algorithm called adagrad, it turns out that if you do adagrad for this problem, you get the bound that I wrote. And that's not with the same constants, but at least up to order, I mean, up to like fixed constants, you get the same bound. So that's like the exact algorithm. You could, of course, also run Cower's algorithm, but if the order of ITJT is not given to you in advance, to run the exact algorithm can get really complicated. Because if you actually write down the strategy, I guess it was here at some point, which was given by these P's, they contain these supremum over trees that's not computable efficiently. Okay. Right. So, I mean, in the tree, I think the first thing that should deter you is the fact that you have a tree, supremum over a tree. That's very, very hard. So I will give you some strategies to kind of get rid of that, but we'll come to it. Mm-hmm. So, okay, so here, okay, so the question was in all of these. So first of all, in the betting game, it's not an expectation, it's a deterministic strategy. So I actually get a deterministic strategy with that bound. For the coerce result, it was an expected bound. It turns out that pretty much for any of these problems, if you can show an in-expectation result, you can also convert it to a high probability result. So the question is whether the strategy is is efficient or not. But if it is efficient, you play the exact same strategy, but instead of looking at the expected regret, look at the exact strategy and then use basically like a martingale difference sequence kind of concentration bound. Like if you use a Hovding-Azuma, you get the same bound with an extra additive factor of square root n with a log 1 over delta, whatever. So that's kind of the standard thing that you can use. Where this gets trickier is if you want these faster rates. So there are, all of this, I've only shown square root n type of rates. It turns out that you can crank this mechanism, but more carefully to get the faster rates. There, the concentration parts become much more trickier. Faster rates as in, if you want, for instance, constant regret or log n regret. Right? Huh? Yeah, you can get those as well. So for instance, here, the betting game is like linear, so you shouldn't expect better than square root n. But imagine that instead of this betting game, I have this game where I'm predicting under square loss. So in this case, you should expect a much faster result. So typically, if script f was finite, then I would get a square root log cardinality of f type of result. So with no n dependence, or basically like log n dependence. No n dependence for if it is finite. If it is like, let's say, linear regression, I get like a log n dependence, d log n or whatever. So roughly speaking, the loss is curved, right? So in some sense, whenever the loss is curved, so if you think, okay, maybe let me actually do this stuff. And as I finish this stuff, I'll tell you where the fast rate could come from, because it'll be easier once I do this. Okay, so right now, let's look at the same problem, okay, except that I'm no longer looking at a betting problem. Now, one caveat here is that whatever strategy that I'm going to give you, it'll only be an upper bound. Okay, like up to now, it was all min-max optimal in that I derived the exact optimal bounds. Now it starts to become a bit of an upper bound, but that's fine. Like we can show that for most of these commonly used losses, you can get lower bounds up to constant order. So it's not too bad, but it's not the exact optimal strategy. So we're going to look at a more general case where your script f is again some model class that takes an input and gives you a real number as output. And now, instead of just taking the linear loss, you have some loss denoted by L here. And on every round, what happens is the context xt is given to us. We pick a prediction y hat t that's real. Then the outcome for that round zt in an arbitrary space is given to us. And then we suffer the loss L of y hat t comma zt. Okay? So zt can be from an arbitrary space. Our prediction is represented as a real number. Now, I'm going to make one assumption that the loss L is convex in its first argument, that is in y hat t, and it's L Lipschitz. Okay, if any of you here unaware of what Lipschitz means, So it just means it's continuous. And if two instances are input instances are close, the outcome is also like up to like constant times the difference, okay, in magnitude of the difference. Okay, so if you have a loss that's convex and Lipschitz, and that's the assumption on the loss that I'm making, and what we are interested in is sum of my losses minus the loss of the best benchmark, okay? So this one is more general than this is a linear betting problem. It turns out that you can do a nice reduction here. So specifically start with our regret that we want, which is this guy, and I'm going to slightly rewrite it. I'm going to pull this minimum or infimum outside the minus, write it as a supremum here. But now, lo and behold, I can use convexity to say that each of these differences is upper bounded by the derivative of y hat t comma zt times y hat t minus f of xt, right? This is just convexity, right? So the tangent is below the function that's kind of rewritten in this form. And now the next thing I'm going to do is I'm going to do a little bit of interpretation here. So what is this derivative L of y hat t comma zt? That is some number that's between minus capital N and capital L. Why? Because I assume that the loss function is L Lipschitz, which means that the derivatives are bounded by capital L. So it has to be between minus L and capital L. And now what I'm going to do is instead of treating this as a number between minus L and capital L, I'm going to treat this derivative as if it's an expectation of a variable that's either -1 with +1 with this probability and -1 with the remaining probability, right? So here BT is a random variable that's +1 with this probability and -1 with the remaining probability. And now the idea is that if I look at expected BT, that's exactly this value out here, okay? And once I do this, expectation is inside the supremum. I can always pull it out. That's Jensen's inequality. So supremum of expected is upper bounded by expected of supremum. And so lo and behold, what I have here, and once I rewrite this supremum back in here, is that my regret, the original regret that I started with, is upper bounded by L times the expected regret, where in here, I just have a bit prediction problem where BT is either +1 or -1. What this means as a reduction is that on every round, I first play, I play y hat t, I get zt. And then what I do is instead of treating it as though I played the loss L of y hat t comma zt, I'm going to basically compute the derivative of the loss with respect to y hat t comma zt. I'm going to draw BT according to this distribution, and I'm going to feed it to the bit prediction algorithm that I had. So this means that if you can do bit prediction well, then you can get an algorithm that works at this generality here for a general convex loss out here. And we already know what's the best bound I can get for this bit prediction problem, right? In other words, essentially what we have shown is that for any online supervised learning problem with a convex L Lipschitz loss, I get an algorithm using bit prediction that tells me that my regret is upper bounded by L times the sequential Rademacher complexity. And to some extent, this is not improvable because we know that for linear losses, this is the best we could have gotten, right? And that's that. And the next thing to also note is that you need a slightly bit more complicated technique. So the typical, if you look at a classic book on statistical learning theory, the way you get Rademacher complexity is through this idea of symmetrization. It turns out that you can do this kind of symmetrization in a sequential fashion. It's a slightly different form of proof, but you can do that. And it turns out that if you did that, then you don't even need the losses to be convex. Give me any loss that's L Lipschitz in its first argument, I can claim the same result out here with different constants and so on. Okay, so it turns out that kind of in terms of like the best bound achievable or up to constant order the best bound achievable, we have our answer that for a fairly general set of sequential prediction problems, the best bound is given by this sequential Rademacher complexity. Okay. Yeah. So I use convexity as well, right? The convexity was the first thing to kind of go from here to here. Yeah. You mean for here as in? Yeah, it was bounded and then I kind of treated it as if it was an expected variable, right? So I had a number that was between minus L and L. I treated it as an expected value of a number that's either plus L or minus L. The problem is for the general case, are you asking about the case where I remove convexity? Right. So that was, so the thing is here, when I do all of this, I'm producing a yt that's binary, right? There, the problem was that y hat t had to be either +1 or -1, right? So this trick that you're doing here works for yt because you're just going for an upper bound. For y hat t, it's not clear how to do this. So the technique that kind of removes this convexity is completely different. It goes through like a different style of min-max analysis. I really don't want to go into that because it's a lot of notation. Mm-hmm. So not really, right? Like, I mean, so the bit prediction is linear in Q, but the problem is it's not that you only need linear in Q, you also need that Q should be a number between 0 and 1. And the problem is once you take, like if you compute the Q there, it comes as a difference of fees. If you don't have the restriction that the difference of fees is bounded by 1, then this value could not be within 0 and 1. Right? And now if it is not between 0 and 1, if you kind of go through this, like kind of, I did this step backwards, right? Like start from nth step, go backwards. Now imagine that I had the restriction that y hat n had to be between 0 and -1 and 1. If I had that restriction, then this solution here where I just equate the two maxes that I had, that's not going to work because that number could be outside, right? Then you have to ask, okay, what is the best y hat n? The answer at the nth step is easy, just clip it at wherever it is, right? But the problem is once you clip it there at n minus 1th step, you're going to deal with the fact that you have supremum over x and then some clipped version there, right? That's already fairly nasty. But imagine you kind of keep doing this up to like the tth step or like the first step, right? Now you're not just going to have the simple nice expectation, you're going to have all of these clips in there that gets like exponentially ugly, right? So you can't really keep track of it. At that point, in some sense, it's as good as just saying, I'm going to write down min-max, kind of the value of the game, of the sequential game. So here, the nice thing is because we had this regularity assumption or because we looked at linear betting, we were able to kind of reduce the sequence of mins and maxes between the two players into something that was just like a simple, nice stochastic quantity. Okay, I guess given that the time is over, just a glimpse of what I wanted to kind of cover in the next lecture. As of now, we've been looking at kind of what's the min-max value or kind of what's the best I could achieve. And while kind of Cover's result gave us like an algorithm, but not necessarily like an efficient algorithm, as we already saw, once the problems get more complicated, it's not clear how to get efficient algorithm. What we are going to do kind of for the next lecture, at least for some part of it, is to come up with algorithm design principle where we are not necessarily going for the min-max algorithm, but we want to say, maybe I still want to get up to constant of the min-max kind of bounds that I can get, but maybe using some kind of ideas of relaxation, I might be able to get efficient algorithms for these problems. And what we'll also see is through these mechanisms, it turns out that all of like the favorite online learning algorithms that were there before, things like gradient descent and exponential weights and so on, they can all be seen as kind of coming out of this mechanism. And you can get much more than that. And through that, we'll kind of move a little bit more into the optimization side. Right? Thanks. Uh-huh.
So, is there any connection between the sequential and the non-sequential versions of the complexity?
Yes, there are. So, okay, so the question was, is there connections between sequential and Mucker complexity and the classical statistical one? The answer is quite complicated. So there are function classes for which the sequential complexity does not even converge, as in it's like order linear in n, but the classical one does converge. But it turns out that for a lot of the practical ones that we look at, they turn out to be the same. Okay, so the simplest one where the sequential and the non-sequential are very different from each other is just the threshold function, right? So the threshold function for the statistical one, you get a square root d times n. That's classic VC theory tells us that. But in the sequential world, that's not true. The reason for that is you give me like the interval 0 to 1. I basically kind of, I would give, the first instance I'm going to give is x1 is equal to half. Okay, let's say you say it's plus. If you say it's plus, I'm going to kind of make sure that you're wrong. I'm going to just decide that the minus, like the threshold is going to be to the right of you. Okay, and then now you decide the next one. And the thing is, because I can kind of, I'm going to kind of keep on going with these dyadic intervals. And because I can do it for infinite precision, I can inflict a sequential Rademacher complexity that's like n over 2 or whatever. Yeah. So in that case, they are very different. But if you look, for instance, for linear classes or for most classes that we typically think about, it turns out that it's the same, up to at least constant order. And there is, at least for kind of large classes of, if you think about script f as being like a unit ball in a Banach space, then the question of whether, and you're thinking about linear losses, the question of whether the two match or not is, it's related to this fairly deep kind of question in kind of Banach space theory, which has got to do with martingale types and types. So it turns out that kind of the analogous, so in classical statistical learning, kind of X's are IID, or kind of where you think about IID instances and uniform convergence. This one is exactly equivalent to the version where you think about martingale sequences and uniform convergence. And the difference between when martingale uniform convergence holds and when IID uniform convergence holds was a question that took fairly long time for kind of the big names in Banach space theory to resolve. So it turns out that they can be different, but it also turns out that the kind of spaces where they are different are really crazy. So it for typical spaces that you would, Banach spaces that you would encounter, they are the same. So I guess my answer to you is, if you have like discrete problems like thresholds and so on, then they can be different. But if you're thinking about more like kind of continuous function classes, typically they are the same. I would say for most practical cases, they're going to be the same. I don't know if that was an answer or a non-answer, but it turns out that it's not, yeah. Yeah, sure. Yeah. Huh? From, you mean the convex to the bit prediction? Yeah. So, I mean, so for to kind of answer the question of is the bound tight or not, and I guess this also goes back to your question, in that the step where I used convexity was, so to answer you kind of, if I don't make any, if I just say L can be any arbitrary convex function, in that sense, yeah, sure, because L being identity is a convex function, it's linear, and in that case, it's all exact, right? But of course, if L has a lot of structure, right? So one way for which L to be convex and the bound to be really bad is if L is just constant function, right? If L is like a single constant function, then yeah, sure, like it is convex, it's whatever you want, but then regret in this case is going to be 0, and the upper bound is really loose, right? So you need to say what kind of L. It turns out that for the classical L's that you have, like logistic loss up to like the right constants, for absolute loss, for hinge loss, all of these, it turns out that it's tight. For squared loss and kind of where I was talking about fast rate, it turns out that it's not tight. And you can kind of, I mentioned about the curvature of the loss leading to the fast rate, right? That's because if you remember where we use the first step where we use convexity, we basically said the difference is upper bounded by gradient times the difference of the inputs, right? But if the loss was curved, from this you can subtract some quadratic term, right? And that quadratic term between of the difference that you can subtract, if for instance it's strongly convex, that subtraction is what gives you the faster rate. You can make use of that, and that gives you like a better rate. So if you kind of use that along with kind of some of these tools, but slightly more carefully, you can get like the faster rate. Any other? Huh?
Is this notion of Rademacher complexity, the sequential one, is that same as or different from Little
A little stone dimension?
Yeah.
Yeah. I mean, so VC dimension is to statistical Rademacher complexity is as Littlestone dimension is to sequential Rademacher complexity. So the Littlestone dimension is kind of the analog of VC dimension, and the sequential Rademacher complexity is the analog of statistical Rademacher complexity. And so just like how VC dimension is kind of a very pessimistic bound, like VC, so Rademacher is also, I'm not saying that, I'm not by any measure, am I saying that Rademacher is not pessimistic, but at least Rademacher is data dependent, VC is not. Similarly, Littlestone is not really data dependent. The sequential Rademacher can be made adversary dependent, but it requires a little bit more work.